Computers are amazing, and they keep getting smaller, cheaper, and more powerful. Moore's law states that the power of classical computers should grow exponentially with time, and it has proven to be correct year after year. However, there is a physical limit to how fast a computer can be, and we are quickly approaching it. Just like everything else in physics, there is a limit to how fast information can travel, and thus how fast a computer can process information.
Does it really matter if computers stop getting faster? Sure, computers are capable of amazing things, but even at their most powerful limits put in place by the laws of physics and information theory, there'll be certain problems that they simply can't solve.
The laws of physics put a limit on how fast a computer can be, and theoretical computer science tells us that there are some problems that involve so many steps that even the fastest of computers would take billions of years to solve them.
In computer science, problems are grouped into classes based on their complexities. Most of these complexity classes contain countless problems that will never be solvable using classical computers. These are useful problems too. Take protein folding, for example. Normal computers really struggle with it, but if they could do it efficiently, we could cure cancer. Luckily, the strange world of quantum mechanics may offer a solution. Quantum computing. There are two main kinds of quantum computers, and they both have the potential to revolutionize the way we solve problems. In quantum mechanics, the state of a system is represented by an object called a state vector, which is just a fancy way of saying that the quantum state can be in several classical states at once. This is called superposition. For classical computers, the most basic unit of information is the bit. Because of superposition, quantum computers can work with quantum bits, which can be in a mix of 0 and 1 at a given time. This allows quantum computers to manipulate all the possible configurations of the bits in a problem at once, just like the data is being processed more densely, speeding up calculations. The first kind of quantum computer is called a quantum annealer. Annealers are the less complex of the two types, which makes them easier to create in the real world. However, this simplicity means that annealers can only solve very specific kinds of problems, known as optimization problems. The goal of an optimization problem is to find the optimal configuration of many variables, like deciding which products you should buy to save the most money. Annealers encode optimization problems on a set of qubits. They use the fact that all systems in physics, even quantum ones, tend to collapse into the lowest energy state. The annealer lets the set of qubits collapse into a low energy state, which can be used to determine the optimal configuration for the problem. Annealers are really efficient at solving optimization problems. However, if we really want to take advantage of the power of quantum computers, we need to look at the second kind, universal quantum. Universal quantum computers are the more ambitious of the two kinds of quantum computers. Where annealers simply let quantum mechanics do the calculations for them, universal quantum computers aim to manipulate those quantum systems. Classical computers change the states of bits when they do calculations, and similarly, universal quantum computers manipulate the quantum states of qubits. Because quantum states are vectors with a sort of direction like a dial in this meter, changing the state of a qubit is like rotating a vector state.
Quantum computers consider all states in parallel, so they aim to rotate probability vectors in such a way that paths to the correct answer constructively interfere. This method of problem solving makes universal quantum computers much more universal than quantum annealers. With quantum technology, we could solve previously unsolvable problems, ranging from curing cancer to making traffic jams a problem of the past. Their potential is virtually boundless.
We're still in the early stages of the quantum revolution, but it won't be long before quantum technology is changing the world.